Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Picture an object out in the freezing absolute void of space.
Right.
A massive, jagged, imposing chunk of material, roughly the length of 8 American football fields, just laid end to end.
It's massive.
Yeah, it is a literal mountain drifting hundreds of millions of miles away in the dark.
And, normally when we model the dynamics of these celestial bodies, we envision them moving with this slow, ponderous grace.
Like a lazy tumble through the vacuum.
Exactly. A slow geologic tumble. But not this one.
No, not even close. This absolute behemoth is spinning so violently fast, completing a full 360-degree rotation every 1.88 minutes.
Which is just wild to even think about.
It completely shatters the fundamental mathematical models of astrophysical structural integrity.
It really does. I mean, we are talking about angular momentum on a scale that turns a sub-kilometer rock into, the equivalent of a blender blade the size of a skyscraper.
Right. And by the classical rules of gravitational binding energy, it just shouldn't exist.
No, it shouldn't. The sheer centrifugal forces at its equator should have overcome its internal gravity and ripped it apart into a massive expanding cloud of space dust eons ago.
But it's there.
Yeah, the structural physics at play are completely unforgiving.
Uh-huh.
When you look at the classical models of how we understand bodies in the main asteroid belt, the math simply does not support an object of that mass surviving that kind of rotational stress.
And yet the data is unequivocal. It's out there.
It's defying the classical limits of centrifugal force.
And its mere existence is forcing the astronomical community to completely reconstruct the physical parameters of what is actually drifting around out there in our immediate cosmic neighborhood.
Exactly.
So the mechanics of how a structure like that stays intact under such extreme torsion is exactly what we're getting into today for you.
It's a huge paradigm shift.
Oh, absolutely. We're looking at the breathtaking and honestly structurally baffling early data emerging from the engineering and commissioning phases of the Vera C. Rubin Observatory.
Which was just published in early 2026.
And what we are really examining here is how the absolute bleeding edge of photometric engineering, specifically this massive 3.2 gigapixel LSST camera, is fundamentally rewriting the textbooks.
And doing it before the observatory is even officially fully operational, which is the crazy part.
Yeah. We are uncovering an entirely hidden population of indestructible, hyperspinning main belt asteroids.
And we're looking down the barrel of an unprecedented flood of real-time astronomical data processing.
It fundamentally alters the timeline of human observation.
The timeline aspect is precisely what makes the Rubin data so anomalous, I think.
Because we aren't even looking at the main event yet.
Right. The Vera C. Rubin Observatory, which is situated high up in the Chilean Andes on Cerro Pachón.
Beautiful location, by the way.
Oh, stunning. But it was explicitly engineered to conduct a legacy survey of space and time.
The LSST.
Exactly. And the entire architecture of the facility is built around the 8.4-meter Simone Survey telescope.
Which, just to give you a sense of the light gathering power we're talking about, an 8.4-meter primary mirror is roughly the width of a 3-story building.
Yeah, and it was spin cast in a rotating furnace at the University of Arizona just to create this uniquely complex, deeply curved honeycomb structure.
It's an engineering marvel all on its own.
It really is. And attached to that optical assembly is the LSST camera.
The current record holder for the largest digital camera ever constructed.
Right. I mean, the focal plane alone consists of 189 individual charge-coupled devices.
The CCDs.
Yeah, CCDs, cooled to minus 100 degrees Celsius to eliminate thermal noise.
Just massive scale.
But these paradigm-shifting discoveries about indestructible, hyper-spinning metallic mountains, they're entirely a byproduct of the commissioning phase.
Right, the engineering phase. And that's what highlights the sheer leap in technological capability here.
Yeah.
Because the commissioning phase is essentially just the telescope clearing its throat.
It's a calibration run.
Exactly. It's the engineering teams doing test patterns, aligning the secondary mirrors, verifying the cryogenic cooling on those 189 CCDs.
Just making sure the initial data pipelines are actually passing information correctly.
They haven't even officially initiated the 10-year continuous survey.
And the telescope is already generating a completely unmanageable deluge of discoveries.
Which naturally forces a necessary evaluation of historical sky surveys, right?
Absolutely.
Because we've been conducting extensive mapping of the sky for decades.
Centuries, if you count early optical telescopes.
Right. We had the Palomar Sky Survey, we have the Sloan Digital Sky Survey, Pan-STARRS in Hawaii.
Not to mention orbital space telescopes for over 30 years.
So if there are massive, hyperspinning metallic needles in the inner solar system, the fact that they remained entirely invisible until a commissioning run in 2025?
It demands an explanation of the previous observational blind spots.
Yeah. I mean, why are we just seeing this now? It's like upgrading from peering through a tiny peephole on your front door to suddenly having a massive bay window.
That's a great way to put it.
You suddenly realize your front yard is full of things you never even noticed were there.
Yeah, and to understand those historical blind spots, you really have to look at the inherent compromises dictated by optical physics.
And sensor limitations prior to the LSST.
Right. Historically, optical astronomy has been defined by this zero-sum trade-off.
Like a seesaw.
Exactly. If you want to look incredibly deep into the universe, say, to capture the faint light of a distant galaxy, or a very small, very dark rock in the outer asteroid belt.
You need a massive telescope with a long exposure time.
Right. But that heavily restricts your field of view to a tiny, microscopic patch of the sky.
It's the equivalent of trying to map the entire Pacific Ocean while looking through a drinking straw.
Exactly. And conversely, if you want a wide field of view to scan large swaths of the sky for moving objects, you typically have to sacrifice aperture and depth.
So you only catch the brightest, most obvious objects.
Right. The engineering triumph of the Vera C. Rubin Observatory is that it violently eliminates that compromise.
It just throws it out the window.
Yeah, it achieves an unprecedented unification of three distinct observational parameters.
Immense depth.
A massive 9.6 square degree field of view.
And critically, a relentless high-frequency cadence.
The cadence is the key.
Yeah, the cadence is the variable that changes the game for transient and moving objects.
Absolutely.
Because it's not just taking a wide, deep picture. It's taking that same wide, deep picture of the exact same coordinates repeatedly.
With very little downtime.
Right. Previous surveys like Pan-STARRS were casting a very wide net, but the physical mesh of that net was too wide.
And the temporal gap between casting the net on the same patch of sky was far too long.
So if you have an object that is incredibly faint, moving rapidly, and changing its brightness profile on a minute-by-minute basis...
it easily slips through the temporal gaps of a slower survey.
Right. But Rubin is essentially establishing a continuous, high-definition optical dragnet across the entire southern hemisphere.
Exactly. And that high-frequency optical dragnet is what captured the benchmark anomaly that is currently dominating the discourse.
The star of the show.
Main Belt Asteroid 2025 MN45.
Okay, let's lay out the precise physical parameters of 2025 MN45 for everyone, because the dimensions versus the kinematics are where the physics just totally break down.
They really do.
The photometric data places its diameter at roughly 710 meters.
So roughly 0.44 miles across.
What a big chunk of rock. But the kinematic data is the absolute shocker.
Yeah.
This 710-meter mass is completing a full rotation every 1.88 minutes.
Which is staggering.
If you calculate that out, this structure is undergoing roughly 765 full rotations every single Earth day.
And that rotational period is what places 2025 MN45 entirely outside the accepted boundaries of the spin barrier.
The spin barrier for main belt asteroids.
Right. And to contextualize why a 1.88-minute rotation is fundamentally impossible under classical models, we have to look at what an asteroid of this size actually is.
Or what we thought it was.
It's exactly. For the last few decades, especially reinforced by sample return missions to asteroids like Ryugu and Bennu.
Incredible missions, by the way.
Oh, absolutely. But the consensus from those missions has been that the vast majority of asteroids larger than a couple of hundred meters are rubble piles.
Right. They're not solid, contiguous monoliths.
No, they are macroporous aggregates.
Essentially just floating, loosely bound collections of boulders, silicates, pebbles, and dust.
Stuff that is just accreted together after ancient collisions.
So the only force holding a rubble pile together is its own incredibly weak collective microgravity.
Which means the structural integrity of the object is entirely dependent on gravitational binding energy.
And gravity at a sub-kilometer scale is practically non-existent.
Yeah, if you were standing on the surface of a 700-meter rubble pile, the escape velocity would be so low you could literally achieve orbit just by jumping.
That's a fun image. Just jump and you're in space.
Right. But because the gravitational binding energy is so fragile, there's a rigid, mathematically defined speed limit for how fast a rubble pile can rotate.
Before the outward centrifugal acceleration at the equator exceeds the inward gravitational acceleration.
Exactly. We call this critical threshold the spin barrier.
Right.
And the formula for critical density dictates that for typical silicate rubble piles, the absolute maximum rotation rate sits right around 2.2 hours.
So 132 minutes.
Right. If a macroporous asteroid spins even a fraction faster than one rotation every 132 minutes, the centrifugal forces dominate.
The object loses cohesion.
The rocks at the equator achieve escape velocity, and the entire structure simply dissipates into a trailing cloud of debris.
I always picture it like spinning a completely wet tennis ball, you know?
Oh, that's a perfect analogy.
You spin it slowly, the water stays on, but you spin it fast enough, and eventually the water just violently flies off in every direction. But the mathematics of centrifugal force, specifically mass times angular velocity squared times the radius, means that the outward force increases exponentially as you drop the rotation time.
Yes, it's not a linear scale.
Right. So we aren't looking at an object flirting with the 132-minute barrier.
No, 2025 MN45 is rotating in under 2 minutes.
It is rotating more than 70 times faster than the maximum theoretical limit for a rubble pile.
Which is exactly why it hasn't disintegrated into a cloud of space dust.
Well, why hasn't it? If the gravitational binding energy is outmatched by a factor of 70, then gravity is entirely irrelevant to this object's cohesion.
Completely irrelevant. The internal physical strength required to hold that mass together against that level of angular momentum.
It's more akin to the tensile strength required to build a space elevator cable.
Yeah, we're no longer talking about gravity. We're talking about extreme material tensile strength.
That is the inescapable conclusion the physics demand.
It is. The fact that 2025 MN45 survives this rotational stress profile definitively proves that it possesses immense internal cohesive strength.
It categorically cannot be a rubble pile.
No, it represents a completely different class of physical object,
which completely invalidates the ubiquitous rubble pile paradigm for objects in this size regime.
It really forces a total rethink of asteroid anatomy.
Right, because if it's not a loosely accreted pile of silicates, the immediate question is material composition.
What is it made of?
Exactly. What specific material can withstand that sheer rotational stress without fracturing? We are obviously looking at something contiguous.
And the structural requirements drastically narrow down the compositional possibilities.
Yeah.
The baseline hypothesis is that it could be a monolithic chunk of highly competent, unfractured silicate rock.
Okay, solid rock.
Alternatively, some models suggest an intensely cohesive, tightly packed clay-like material bound by complex hydration processes.
Like cosmic cement.
Exactly. However, the most physically robust hypothesis, and the one that effortlessly satisfies the extreme tensile strength requirements, is that we are looking at a solid metallic core.
Composed primarily of an iron-nickel alloy.
Right. Furthermore, the photometric analysis published by Dmitry Vavilov and the research team adds a critical geometric complication.
Oh, the shape.
Yeah. The light curve amplitude of 2025 MN45 indicates that the object is not remotely spherical.
It is highly elongated.
Its aspect ratio suggests its effective length could actually approach a full kilometer across its longest axis.
Wait, so the morphological reality is a 1 kilometer spinning needle?
Yes.
The physics of that geometry make the survival of the object even more astounding.
Oh, absolutely.
Because if you have an elongated structure rotating around its center of mass once every 1.88 minutes, the centripetal acceleration acting on the far tips of that 1 kilometer needle is orders of magnitude higher than if it were a compact sphere.
The leverage is insane.
Right. The sheer mechanical shearing forces acting on the center of the object would snap almost any standard terrestrial rock right in half.
Just cleanly break it.
The fact that a 1 kilometer structure remains intact under those shearing forces heavily points toward a metallic composition.
It really does. We are talking about the kind of crystalline iron-nickel structures, like the Woodman-Stetton patterns we see in certain meteorites.
Right, those beautiful crosshatch patterns.
Exactly. And those only form when molten metal cools incredibly slowly over millions of years.
Which brings us directly to the implications for early solar system evolution.
Because you do not spontaneously form a 1 kilometer solid chunk of highly structured iron-nickel alloy from the gentle accretion of protoplanetary dust.
No, you need a forge for that.
Right. Monolithic structures with that level of density and tensile strength are the physical byproducts of planetary differentiation.
So early in the chaotic formation of the solar system, there were these massive protoplanets.
Planetesimals large enough that their own radioactive decay and gravitational pressure caused them to completely melt.
And during this molten phase, the heavy elements like iron and nickel sank to the center to form a dense metallic core,
while the lighter silicates floated up to form a rocky mantle and crust.
So to get a 1-kilometer shard of that pure core material drifting freely in the main belt,
you require a violent, catastrophic mechanism to strip away hundreds of kilometers of solid rock mantle.
Exactly. These hyper-spinning monoliths are likely the surviving shrapnel of utterly destroyed worlds.
It's a bit poetic, really.
It is. If two massive differentiated protoplanets collided at high velocity during the chaotic early days of the solar system,
the impact would have shattered their mantles and fractured their exposed metallic cores into fragments.
So 2025 MN45 is, in all probability, a fractured piece of a dead world's heart, just wandering the inner solar system for the last 4 billion years.
It is the ultimate survivor of a cosmic demolition derby.
I love that, a cosmic demolition derby. But what makes this finding so destabilizing to current models is the scale of the population.
Right.
Because if 2025 MN45 was a singular anomaly, just one random iron needle tumbling through the dark, it could be categorized as a statistical outlier.
A freak accident of celestial mechanics.
Exactly. But the data unequivocally demonstrates that it is not alone. Far from it.
And this is where the sheer, unadulterated processing power of the Rubin Observatory pipeline becomes the focus.
Because this entire revelation, the destruction of the spin barrier consensus, was derived from a microscopic sliver of observation time.
Which is wild. The researchers pulled this data from just 10 hours of active observation,
spread out over 7 nights during April and May of 2025.
In that incredibly brief 10-hour window, Rubin identified nearly 2,000 previously unknown main belt asteroids.
And roughly 1,900 of those were confirmed as entirely new discoveries.
The yield from that 10-hour window is just staggering.
It really is. And embedded within that sample of 1,900 new objects was an entire, previously undetected population of extreme rotators.
A whole hidden population.
Yes. The photometric pipelines identified 19 super-fast rotators.
Meaning asteroids that cleanly and undeniably violate the 2.2-hour spin barrier.
Exactly. And even more profoundly, the pipeline flagged 3 ultra-fast rotators,
which are massive objects completing full rotations entirely under the 5-minute mark.
Under 5 minutes. The specific kinematic profiles of these ultra-fast objects establish a definitive gradient of structural integrity across the main belt.
Right. It's not just one rock.
Exactly. Beyond our benchmark of 2025 MN45, the pipeline flagged 2025 MJ71, exhibiting a rotation period of approximately 1.9 minutes.
You look at 2025 MK41 rotating every 3.8 minutes.
We've got 2025 MV71 sitting at roughly 13 minutes.
And 2025 MG56 at about 16 minutes.
And these are all objects hundreds of meters in diameter.
Which completely inverts the assumed rarity of these monolithic structures.
Right. We're looking at a scenario where highly cohesive, indestructible, hyper-spinning fragments are not statistical anomalies.
They are a highly common, ubiquitous population within the main belt.
They were simply invisible to previous surveys because our sensor integration times were too slow and our cadence too relaxed.
Exactly. We just weren't looking fast enough.
But identifying the population immediately introduces a secondary kinematic puzzle.
The why.
Right. We know what they are, and we know they possess the tensile strength to survive the rotation.
But what is the precise physical mechanism injecting that massive amount of angular momentum into these specific bodies?
What is spinning up a 1-kilometer mass of iron to a 2-minute rotation?
Well, to isolate the mechanism driving that extreme angular momentum, you really have to analyze the long-term thermodynamic environment of the solar system.
Okay.
There are kinetic mechanisms, of course. A highly off-center oblique impact from a smaller piece of debris can transfer substantial angular momentum.
Basically spinning the object up like a billiard ball.
Right. And for objects whose orbits intersect the inner planets, tidal shear forces during close planetary encounters can also induce rapid rotation.
But those are situational.
Exactly. Statistically, the most elegant, pervasive, and continuous mechanism acting on the main belt is a subtle thermodynamic interaction known as the URP effect.
The URP effect, that's an acronym, right?
Yes, it stands for the Yarkovsky-O'Keefe-Rzhevsky-Paddock effect,
which combines the orbital drift theories of Yarkovsky with the rotational torque mechanics developed by the latter 3 physicists.
That's right. And the thermodynamics of the URP effect represent one of the most Counterintuitive, yet mathematically beautiful mechanisms in astrophysics.
Because the premise is that ambient sunlight photons with absolutely zero rest mass can exert enough physical torque to spin a billion-ton metallic mountain up to a 2-minute rotation.
Which sounds impossible.
It requires a deep dive into radiation pressure and anisotropic thermal emission.
It entirely revolves around the principles of thermal inertia and photon momentum.
Okay, break that down for us.
So, while photons are massless, they carry momentum governed by their energy.
Right.
When solar radiation impacts the surface of an irregularly shaped asteroid, the surface material absorbs that electromagnetic energy and heats up.
Like asphalt on a sunny day.
Exactly. And as the asteroid naturally rotates, that heated surface area turns away from the sun and faces the near absolute zero temperatures of deep space.
So to maintain thermodynamic equilibrium, the asteroid radiates that stored heat energy back into space in the form of infrared photons.
Right. But because the asteroid is a jagged asymmetrical fragment like our 1-kilometer needle with ridges, craters, and massive structural deformities.
That thermal radiation is not emitted uniformly in all directions.
Exactly. The anisotropic, or uneven geometry of the asteroid means the infrared photons are emitted at various angles relative to the asteroid's center of mass.
So every single infrared photon radiating off a tilted ridge carries away a microscopic fraction of momentum.
And in the frictionless vacuum of space, this acts exactly like an array of incredibly weak, continuous thrusters mounted asymmetrically across the asteroid's surface,
creating a microscopic net torque.
Yes. Now, over the span of a few days or even years, this thermal torque is entirely negligible.
You wouldn't even notice it.
But the ORP effect is cumulative.
Ah.
When you apply that continuous asymmetrical thermal thrust over a timescale of tens or hundreds of millions of years, it gradually and relentlessly accelerates the asteroid's rotation.
It's like a slow-motion thermodynamic motor.
Exactly. Taking a slowly tumbling monolithic shard and spinning it up until it hits a blistering 2-minute rotational velocity.
The implication that solar radiation is acting as a continuous thermodynamic engine for millions of main belt objects is just profound.
It's elegant physics.
But the confirmation of that dynamic relies on an observational premise that warrants some scrutiny, I think.
Oh, for sure.
If we are utilizing the ORP effect to explain the angular momentum, and we are definitively categorizing these bodies by their specific rotational velocities, like 2025 MN45, at exactly 1.88 minutes.
How are the octal centers actually deriving that kinematic data?
Exactly. We are dealing with objects that are under a kilometer wide, sitting hundreds of millions of miles away.
Right.
Even with an 8.4-meter primary mirror and a 3.2 gigapixel CCD array, the optical resolution cannot physically resolve the surface geography of these rocks.
No, not even close.
They do not appear as spinning mountains. They appear as a single subpixel point of light on a dark background.
Just a dot.
So what is the specific data pipeline that translates a single dot of light into a highly precise, three-dimensional kinematic and morphological model?
Well, the solution to that observational limitation relies on a highly sophisticated photometric technique known as light curve inversion.
What curves?
Yeah. You are perfectly correct that the telescope is not resolving the surface or the physical shape. The LSST camera is not capturing video of a tumbling rock.
Right.
What the cryogenic CCDs are exceptionally engineered to capture is highly precise photometry, the exact quantifiable amplitude of the light bouncing off that object.
Because the asteroid is illuminated by the sun?
Right. And the amount of photons it reflects toward Earth is strictly proportional to the amount of surface area it exposes to our line of sight.
Okay, so if we take the elongated 1-kilometer needle geometry of 2025 MN45, as it rotates in the vacuum, the cross-sectional area facing the Earth is constantly changing. When the broad 1-kilometer side of the needle is perpendicular to the telescope, it reflects a massive amount of solar radiation, and the photometric brightness peaks.
Right. But 45 seconds later, when the narrow, jagged tip of the needle rotates to face the Earth, the reflective surface area drastically shrinks.
And the apparent brightness drops significantly.
Precisely. And the data pipeline continuously measures that flux in apparent magnitude and plots it against time.
The resulting graph is the light curve.
Yes. I mean, think of a lighthouse.
Oh, I like this. A rotating lighthouse from 100 miles away.
Exactly. But imagine the lighthouse is shaped like a lumpy potato.
Okay, a lumpy potato lighthouse.
Right. You can't see the potato itself, but by timing the flashes of light, how long they last, how bright they get, You know exactly how fast it's spinning and can guess its shape.
By analyzing the periodicity of the peaks and troughs in that light curve, the system mathematically derives the exact rotational period to fractions of a second.
But the light curve inversion process goes far beyond just kinematic timing. Yeah, by mapping the specific slopes of the curve, like how sharply the light drops off, or the asymmetry between the primary and secondary brightness peaks, astronomers can solve the inverse problem.
They can utilize complex algorithms to reconstruct a rough three-dimensional wireframe of the asteroid's shape.
Furthermore, by observing how the light curve alters its amplitude over several months as the Earth and the asteroid shift their relative orbital positions,
we can determine the orientation of the asteroid's rotational pole in three-dimensional space.
Exactly.
But wait, calculating those parameters requires an assumption of uniform albedo, doesn't it?
That's the tricky part, yes.
If the object is a differentiated monolithic fragment, wouldn't the reflectivity of the surface heavily skew the light curve?
It absolutely could.
Like, if one side of the asteroid is a highly reflective iron-nickel alloy and the other side is coated in dark carbonaceous chondrite dust.
A brightness peak might simply indicate a highly reflective material facing us, rather than a larger surface area.
Right, so how does the Rubin photometry pipeline differentiate between geometric cross-section and surface composition?
That is exactly where the multi-band photometric capabilities of the LSST camera become essential.
Ah, the optical filters.
Yeah, the camera doesn't just measure raw photon counts. It observes through a complex array of 6 distinct optical filters, ranging from ultraviolet to near-infrared.
Because different materials reflect different wavelengths of light with varying efficiencies.
Precisely. An iron-rich metallic surface will yield a distinctly different spectral signature across those 6 filters compared to a dark, carbonaceous silicate surface.
So by cross-referencing the amplitude of the light curve across multiple specific wavelengths, the data pipeline can filter out albedo variations from geometric variations.
Yes. In this initial commissioning sample alone, the algorithms were able to extract not just precise rotation periods and elongated shape estimates, but also rough colorimetric and compositional data for 76 distinct asteroids.
Which really just highlights the staggering computational sensitivity of the entire apparatus.
Mind-blowing.
To measure a 1.88-minute periodic fluctuation, correct for albedo variations across 6 spectral bands, and map it to a sub-kilometer object hundreds of millions of miles away.
It requires a margin of error that is practically microscopic.
It requires an optical system that can take continuous high-definition exposures while completely mitigating atmospheric distortion and thermal sensor noise.
And the fact that the engineering teams achieved this level of data fidelity during a mere calibration run is astonishing.
It is, and it perfectly contextualizes the sheer scale of the data processing architecture required to operate the Rubin Observatory.
Oh, definitely.
Because while finding 1,900 new asteroids in 10 hours of observation is a massive scientific victory.
In the context of the observatory's ultimate capability, it is practically a rounding error.
Right. To truly comprehend the paradigm shift Rubin represents, we have to examine the systemic stress test conducted on February 24, 2026.
Yes, the deluge.
On that single night of observation, the automated pipelines processed and issued approximately 800,000 real-time astronomical alerts.
The magnitude of 800,000 alerts in a single night is, well, it's difficult to contextualize within the framework of historical astronomy.
It's just unprecedented.
To understand the computational achievement, we have to define what constitutes an alert within the LSST data architecture.
Okay, let's define it.
The Rubin Observatory does not operate on a traditional model where astronomers manually download images to search for anomalies.
Nobody is sitting there squinting at a screen.
Right, that would take lifetimes.
Yeah.
The entire process is dictated by advanced machine learning and automated image subtraction pipelines.
Image subtraction.
Yeah, every time the telescope captures an exposure of a specific coordinate in the sky, a supercomputer instantly aligns that new image with a deep historical template image of the exact same coordinates.
So the system then mathematically subtracts the static background.
Exactly. Every galaxy, every stationary star, every known nebula is removed from the data.
So the system is exclusively looking for the delta. It isolates anything that has moved, anything that has altered its photometric brightness, or anything that has spontaneously appeared in the sky that wasn't there in the template image.
Precisely. And any isolated delta triggers an alert.
Got it.
But these alerts are not compiled into some daily digest.
No.
They are packaged with their precise coordinates, light curves, and historical photometric data, and broadcast globally to astronomical broker systems within roughly 60 to 120 seconds of the telescope's shutter closing.
Within 2 minutes.
Yes. And these alerts encompass a vast spectrum of astrophysical phenomena known as transients.
Transients, meaning things that change.
Right. It includes near-Earth asteroids streaking across the field of view.
It flags cataclysmic variables, where a white dwarf is siphoning matter from a companion star and igniting in a sudden nova.
It captures the exact moment a distant, supermassive black hole flares as it tidal disrupts and consumes a wandering star.
It detects the massive initial optical flash of a star collapsing into a supernova in a galaxy billions of light years away.
And the system successfully isolated, categorized, and broadcast 800,000 of these transient events in a single evening.
But the truly staggering reality of that February 24th milestone is that it was merely a fraction of the system's eventual output.
Oh, absolutely.
When the 10-year legacy survey of space and time initiates its primary operations, the alert pipeline is explicitly engineered to process and distribute up to 7 million alerts per night.
7 million distinct, real-time astrophysical anomalies every single time the Earth rotates.
It's hard to even wrap your head around that number.
The computational bottleneck completely shifts. The challenge is no longer gathering the light.
The challenge is building an algorithmic architecture capable of filtering a torrent of data that no human being could ever hope to manually review.
The transition from a few thousand alerts per night in legacy surveys to 7 million alerts per night in the LSST era, it forces a total reliance on massive, cloud-based broker systems.
Like Antares and LSST.
Exactly. These automated brokers ingest the massive fire hose of Rubin data and utilize highly trained convolutional neural networks to instantly classify the transients.
They separate the noise from the signal.
Right. If the neural network identifies the specific photometric signature of an early-stage type A supernova, it instantly pings robotic spectroscopic telescopes across the globe,
commanding them to automatically pivot and capture the chemical spectra of the explosion before the initial light curve fades.
It fundamentally transforms the methodology of astronomical observation.
From studying static, historical photographs of the universe to interacting with a dynamic, high-definition, real-time movie of the cosmos.
We are actively transitioning from cosmic archaeology to cosmic live streaming.
That's a great way to put it. But we must address the systemic application of this massive data architecture.
Because why does it matter? Right.
Exactly. A highly detailed analysis of the yo-yo-RP effect, metallic core differentiation, and automated transient brokers is fascinating on a theoretical level.
But how does this immense influx of highly precise kinematic and morphological data apply to the immediate survival of the terrestrial biosphere?
Because the structural integrity profile we mapped out for 2025 MN45 has profound and immediate implications for the discipline of planetary defense.
Oh, the structural data is arguably the most critical metric for near-Earth object impact mitigation.
The core mandate of planetary defense is the early detection, precise characterization, and eventual deflection of any asteroid identified on a collision course with Earth.
And for the last 20 years, the prevailing deflection models heavily assumed that a hazardous impactor would likely be one of the macroporous rubble piles we discussed earlier.
The aggregate gravel pit models.
Right. And the physics of deflecting a highly porous aggregate object present massive engineering challenges.
Because if you launch a kinetic impactor similar to the spacecraft utilized in the DART mission and intentionally ram it into a rubble pile at extreme velocity,
the momentum transfer is highly inefficient.
The kinetic energy of the spacecraft is absorbed and dissipated by the extensive empty void space and the shifting regolith between the loosely bound boulders.
Right. The impact craters the surface, compresses the dust, and perhaps creates a localized plume of ejecta.
But the overall delta V, the change in velocity required to push the asteroid off its orbital trajectory, is severely dampened by the object's porosity.
The physics of momentum transfer, often represented in these calculations by the beta factor, which measures the enhancement of momentum from impact ejecta.
It's entirely dependent on the structural cohesion of the target body.
Exactly. If the Rubin Observatory is conclusively proving that a significant percentage of main belt and by extension, near-Earth objects are not highly porous rubble piles,
but are in fact monolithic, densely packed silicates or solid iron-nickel cores spinning at extreme velocities,
the mathematical parameters of deflection change entirely.
It is the kinetic difference between firing a projectile into a massive pile of sand versus firing a projectile into a solid anvil.
That's the perfect analogy.
If you execute a kinetic impact on a highly cohesive monolithic iron core, the kinetic energy does not dissipate into empty void space,
No, the energy transfers efficiently across the rigid crystalline structure of the metal.
resulting in a much higher conservation of angular and linear momentum.
You can actually push the object off course with a high degree of mathematical predictability.
However, the severe consequence of that structural density applies directly to the impact scenario itself, doesn't it?
Yes, unfortunately. If a mitigation attempt fails, the atmospheric entry physics of a metallic monolith are vastly more destructive than a rubble pile of identical mass.
Because a loosely bound aggregate of silicates will experience massive aerodynamic ram pressure as it hits the Earth's atmosphere at cosmic velocities.
It will likely undergo catastrophic airburst fragmentation high in the stratosphere, dissipating its kinetic energy in a massive shockwave.
Which is bad, but
But a 1-kilometer solid iron core possesses the tensile strength to survive the extreme heat and pressure of atmospheric entry entirely intact.
it will not fragment.
It will deliver the entirety of its kinetic energy directly into the Earth's crust, resulting in a massively deep impact crater and catastrophic global seismic and climatic consequences.
So Rubin's capacity to utilize precise multiband photometry to instantly characterize the density, structural cohesion, and exact rotational state of a newly discovered object within minutes of its detection.
It is a profound leap forward in planetary risk assessment.
The system allows us to instantly differentiate between a loosely bound kinetic sponge and a solid iron cannonball.
Which is information you really want to have before you launch an interception mission.
Yeah, absolutely. But alongside the immediate requirements of planetary defense, there is the broader macro-level application of this data to the study of cosmic history.
Right, because we discussed how these monolithic fragments are the shattered cores of differentiated protoplanets.
So by mapping the sheer volume of these extreme rotators across the main belt, we are essentially tracing the exact isotopic and structural blueprints of the early solar system.
These fast rotators serve as pristine kinetic time capsules.
The fact that a 1-kilometer shard of iron survived the catastrophic collisions of the early solar system,
Endured the chaotic gravitational migrations of Jupiter and Saturn during the late heavy bombardment.
and withstood millions of years of extreme thermal torque from the URP effect.
It means it holds an unbroken physical record of our system's violent accretion phase.
So by utilizing the Rubin pipelines to map their precise orbital parameters, categorize their specific rotational velocities, and analyze their multi-band spectral compositions,
Astrophysicists can reverse engineer the kinematic models of the early solar system.
we can determine exactly how many protoplanets formed, precisely where they were located, and what specific collisional events led to their destruction.
It provides the physical evidence required to validate complex orbital dynamics models like the NICE model, which theorizes the dramatic migration of the giant planets.
The perspective articulated by lead researcher Sarah Greenstreet from the University of Washington and NOR Lab perfectly synthesizes the impact of the Rubin architecture.
Yeah, her analysis centers on the reality that Rubin's unprecedented combination of vast spatial breadth, deep photometric sensitivity, and relentless temporal cadence captures the precise phenomena that historically slip through the observational gaps.
We are crossing a threshold where entirely new classes of astrophysical phenomena are actively being categorized.
The extreme kinematic profiles that we previously assumed were statistical impossibilities.
It's like a solid metallic needle spinning hundreds of times a day.
They're rapidly being recognized as foundational commonplace components of our solar system's architecture.
We simply lacked the optical and computational machinery necessary to observe them.
And it is vital to reiterate that the dataset fundamentally dismantling our understanding of asteroid morphology was extracted from a mere 10 hours of early engineering calibration.
10 hours.
When the LSST fully initiates its decade-long survey, processing millions of alerts per night, the volume of newly discovered main belt and near-Earth objects will reach into the hundreds of thousands annually.
The sheer scale of the morphological and kinematic data we are about to ingest will require a continuous rewriting of astrophysical consensus.
The structural parameters of the universe are about to be mapped with a terrifying level of precision.
To synthesize the massive scope of the data we've explored today, we initiated this analysis with a singular, mathematically defiant anomaly.
A sub-kilometer mass of material drifting in the main belt, subjected to such extreme angular momentum that it completes a full rotation every 1.88 minutes.
A kinematic profile that entirely shattered the accepted parameters of the 2.2-hour spin barrier.
and force the realization that we are observing highly cohesive, potentially metallic monoliths.
The shattered, indestructible remnants of long-dead protoplanetary cores.
Right, and from that single benchmark, we extrapolated a hidden massive population of these extreme rotators.
Their incredible velocities slowly and relentlessly accelerated over millions of years by the asymmetrical thermal emission of the URP effect.
And the entirety of this paradigm shift was captured by a revolutionary 3.2 gigapixel optical architecture in the Chilean Andes that is currently just running its baseline calibrations.
Preparing to flood global data brokers with a relentless torrent of 7 million astronomical transient alerts every single night.
Transitioning our view of the cosmos from a static image to a highly dynamic, real-time kinematic map.
It represents a fundamental evolution in human observation.
We are moving beyond the era of passive localized sky mapping into an era of active systemic real-time monitoring of a highly complex, kinetically aggressive universe.
The observational capabilities are truly entering a new epoch. And I want to leave you with one final, deeply intricate mechanism to consider.
Yeah.
We spent significant time analyzing the thermodynamics of the YRRP effect, the verified physical reality that the microscopic momentum of ambient solar radiation, the gentle, almost imperceptible transfer of heat and infrared photons, can act as a continuous thermodynamic motor.
Slowly and silently spinning a billion-ton mountain of solid metal up to a blistering 1.88-minute rotational velocity over millions of years.
It is an ambient force so incredibly subtle, yet so unimaginably powerful given enough time.
So true.
So, if the sheer pressure of starlight can dictate the extreme angular momentum of the most dense, indestructible objects in our solar system, what other invisible microscopic thermodynamic or gravitational forces are currently operating across the cosmos?
It really makes you wonder.
What other delicate, highly complex mechanisms are actively shaping, accelerating, and destroying the seemingly inert mass at the absolute darkest edges of our solar system, completely outside the bounds of our current physical models, waiting for a camera sensitive enough to finally capture the data?